We are going to keep our focus on just the B cells that need T cell help. We're not going to worry about B1 cells anymore. So moving forward, we're just talking about our traditional B cells that need T cell help. So our follicular helper T cells stayed in the lymph node, and they are going to move then into the B cell area of the lymph node to try to find its match, its pair, its specific antigen that the B cell now is going to be presenting on MHC class 2. Once the T cell then finds that antigen, it's going to form a cognate pair with the, or a conjugate pair with the B cell, and that's called a cognate. And so then this conjugate pair, B cell and T cell, are going to be stuck together and they're going to stay together. And this interaction between the T cell and the B cell requires CD40 binding to CD40 ligand. And then the T cell is able to deliver the cytokines it needs to activate the B cell and get the B cell to start to isotype switch to better antibody than IgM or IgD. So that's what's really happening in this image here, where we have our CD40, our CD40 ligand binding to CD40, and then the cytokines, probably IL-21, being delivered to the B cell. There's other cytokines as well, depending on what type of antibody is needed. But these B cells then will get the cytokines and then start to go through expansion. So once that specific Ig or B cell and T cell form that conjugate pair or that cognate, they'll move from the T cell area or the B cell area down into the medullary cords. And so there's a movement that happens throughout the lymph node, where we had our T cells meet up with our B cells, kind of where the B cell area boundary is, and then move towards the medullary cords, where there's going to be proliferation, differentiation into plasma cells. The B cells are going to divide, and then this will create what's called a primary focus. Now, in the primary focus, that's where lymphoblasts are going to be created, which are going to start to produce IgM in the secreted form. Up to this point, IgM has been bound to the surface as a B cell receptor. But now these lymphoblasts are able to secrete IgM. Some of those lymphoblasts are going to stay in the medullary cords, and they'll differentiate into plasma cells. IL-5, IL-6 will be two cytokines that will drive this production, and those cytokines are secreted by T follicular helper cells to drive these B cells into becoming plasma cells. But again, they're secreting IgM. Other lymphoblasts now are going to move back into the lymph node, into the B cell area. So now they're moving from the medullary cords back into this B cell area. And this is where this cognate pair is going to form a germinal center. And they proliferate and form central blasts. Central blasts then are going to end up being able to make a germinal center where we have tons of proliferation going on, lots of expansion of antigen activated B cells, creating a antigen specificity across a bunch of B cells that can vary slightly, very slightly, very different, because these T helper cells are driving affinity maturation. And so these cytokines that the T cells are making are going to induce the B cells to turn on somatic hypermutation at this point now. So we're not doing the RAG enzymes, but rather we're doing AID. So AID is that enzyme that's going to recognize tiny little pieces in the variable portion to go ahead and switch out tiny little pieces, as well as move, do little addition of nucleotides, and then also switch out IgM for IgD, or you switch out the mu constant regions for and switch out the delta constant regions for gamma, epsilon, alpha, to make IgG, IgA, and IgE as needed. Now, this is a lot of proliferation, a lot of B cells are being made, and because of that, the lymph node becomes enlarged. And that's what we see when you have a swollen lymph node. And so this here, this swollen lymph node, I mean, that's a pretty extreme example, but you've gotten sick before and you could feel where you have swollen lymph nodes, you know, underneath your neck there, underneath where your jaw is, behind your ears, maybe in your armpits, but you might, wherever these lymph nodes are, that you can, you know, feel them externally, you can tell that there's swelling going on, and it's because of all of these extra B cells that are being made. And so it's a germinal center that contains lots of rapidly dividing B cells, but then the T cells are also dividing as well. And so there's a lot of swelling that can go on. Now, the centroblasts are going to become more and more and more packed because of all these cells that are dividing, and they're going to give rise to what we call centrocytes. Don't get lost in these names. I'm putting them out there for you, but it's not as important that you remember all of these names, at least not from my course. Maybe if you're not in my course and you're taking another one, it is important. But these centrocytes will start to express surface Ig, which now can have a different isotype. So potentially there could be IgG, potentially there could be IgA. But then hypermutation can happen where there's going to be some really, really great changes that make the antibody even stronger at recognizing antigen, and maybe some of them aren't as good. But in the end, it's going to have somewhat similar antigen recognition specificities for these immunoglobulin. Some are just going to be better than others because of the hypermutation that happened. And those centrocytes that create the antigen receptors that have the highest affinity for antigen, they are going to be further selected for development and for development into plasma cells. And so then those will be promoted to plasma cells to create that antibody that has the highest affinity for antigen. So here's kind of just a summary image of all of that happening together, where we have our activated B cell that has now brought in antigen, processed it, presented it on MHC class 2. Our cognate T cell has found that antigen, bound CD40 to the CD40 ligand to CD40, has told the B cell to go ahead and start to proliferate and differentiate and go through somatic hypermutation and make a whole bunch of different changes to the antigen specificity. Some of those plasma cells then that make the highest antibody specificity are going to remain in the lymph node to produce antibody that will bind with antigen that comes in through the lymph or whatever it might be. Some of the plasma cells are going to migrate into the bone marrow and produce antibody that gets secreted out through the bone marrow. And so that then puts antibody out into peripheral circulation so that it can bind with antigen no matter where it's at. Now, if a centrocyte fails to obtain and present antigen, meaning it didn't make very good antigen receptors, and the follicular helper cell, they just kind of lose interest in each other, then that B cell is going to go through apoptosis. And it will not be able to survive and and be removed from circulation. So apoptotic centrocytes then are phagocytized by macrophages that are also in the lymph node. And so they're just removed so that there's room for our activated B cells and T cells to go ahead and go through replication and differentiation. So only those centrocytes then that have gone through affinity maturation and have been selected for because they make the best antibody, they make the best affinity for antigen, they are going to be selected for differentiation. They are going to be selected to make plasma cells. And that way, the best antibody is going to be out there. So over time, because of affinity maturation, antibody is going to improve and improve and improve with each, with time, during an infection, but also with each subsequent infection. And so this process then of affinity maturation makes sure that B cells concentrate on only making the best antibody. And if a B cell doesn't make the best antibody, it doesn't get to survive. And so energy is focused only on those B cells that make the best possible antibody, and they're selected to be plasma cells and differentiate. Now, the first immunoglobulin made is IgM, and it's the first one that's secreted. But after activation, B cells then are told to switch, isotype switch. T cells will say, nope, time to make a better antibody, like IgG, IgA, IgE, depending on what the pathogen is. And so this isotype switching, which we've talked about a few times, where we take out the mu and the delta, and we start to use the gammas, we start to use the alphas, we start to use the epsilons, those occur during when the B cells are in the germinal center. And then that isotype that is selected is completely dependent on the T follicular helper cell and what types of cytokine is being produced. So if we have IL-4, that is going to be really great against parasitic infections because it induces this class switching to IgE. If we have IL-5, that is going to be really great for getting IgA, and then for IgG, we want interferon gamma, but like also IL-21 is really great for that as well. So I'm going to okay, sorry, had a little bit of an interruption there. IL-21 is another one in here that can be used to help drive IgG production. Okay, now at the height then, there we go. At the height is for large quantities of antibodies to be produced because they are very central to fighting the infection. The centrocytes that win the affinity selection, meaning those that produced the highest affinity antigen receptor, will go on to leave the germinal center and differentiate into plasma cells. Those plasma cells, their only role is to make antibody. And that's why we see plasma cells kind of always indicated by having a very noticeable Golgi, because there's so much protein being produced and being exported. That's their effector function, is to make antibody. And so these are the plasma cells or the effector B cells that provide antibody for dealing with infections. At least in this point, current infections. But as the infection subsides, so as the antibody works and the cell-mediated arm of immunity works, centrocytes are going to then differentiate into not so much plasma cells any longer, but now into long-lived memory B cells. What's cool about these memory B cells is that they are already isotype switched. They already have gone through affinity maturation, and so they have high affinity antigen receptors. That means that the investment that the cells put into making a high affinity B cell isn't lost. It's there for any subsequent exposure to the same pathogen. And these B cells remain pretty much quiescent. They're not going to be doing anything until reactivated. As soon as they're reactivated, they're going to encounter the same antigen with a very fast response, high affinity isotype switch antibody that can pretty much wipe out the pathogen, antigen, toxin, whatever it is, before you're even notice that you're infected. So that is the whole premise behind vaccinations. So in summary, I have just a little bit of summary here for you, is that the first priority of any infection is speed, right? low affinity, but it's going to be IgM, and it's going to not be very optimal. It might be somewhat useful, but at least it does something. Get it out of the gate. But as the infection continues, the next priority is to make really great antibody. And so that requires improvement of the antigen receptor. It requires somatic hypermutation, which is that affinity maturation. And it requires isotype switching out of the IgM into either an IgG, likely, or an IgA or an IgE. And this is all driven by cytokines produced by the T follicular helper cell. So these guys are vitally important because they will interact with B cells, getting them to make this very important aspect, the whole other arm of the immune system, the humoral immune system. So here's one more summary slide for you that has a B cell compared to a plasma cell, a naive B cell compared to a plasma cell. You can see that the naive B cell has an androgen receptor, but is attached to the surface, where plasma cells are going to secrete it as its immunoglobulin is antibody. Yeah, and so the naive B cell is not going to have any secretion where the plasma cell will, but the naive B cell will go through somatic hypermutation where a plasma cell won't, because it's already been done. Same with isotype switching, the plasma cell won't because it's already been done. Okay, my last summary slide is just a review of the anatomy of a lymph node, where we have our T cells and our B cells and where things happen. And we have our B cell area up at towards the cortex, and we have our T cell area towards the middle, more towards the middle part, right? So anyway, just kind of a review to show this is where the B cells are going through hypermutation, somatic hypermutation, affinity maturation, and then when the best of the best get picked, they get moved to produce antibody, and eventually some of them will go to the bone marrow to produce antibody systemically. Okay, that is what I have then for the second lecture. We will look at, oops, I don't want to kind of keyed you up to it. Here we go. We'll look at effector functions of antibodies then in the next lecture.